Hi students, good evening. Welcome to this video session. I remain Samuel Dominic Chukwu Emeka, aka Some Dumb for Peace. In this video session, we shall discuss your section 5.3 homework assignment. Section 5.3 deals with a binomial probability distribution. Please, before you continue with this video, it is expected that you have read the notes on binomial probability distribution, as well as viewed the videos on that topic. It is also important that you view the videos and the prerequisite videos, which includes videos on probability, videos on probability distribution, prior to continuing with this video. Okay, so it is important that you have read the notes and viewed the videos, then have a good understanding of it. Then you can now view this video and you can do your own assignment. As usual, we are going to use technologies to do this video, and the technologies that we are going to use are my calculator and the Pearson Statcrunch. We might also use the calculator from the computer if we need to. Okay, so let me go ahead and pull up my calculator on Firefox browser. I'm going to type my name, and let's go to the mobile friendly site. So I type my name and I type AppSpot. The first site is mine, and I'm just gonna go to portfolios, or you can go to mathematics, statistics, resources, or I'll just go to portfolios, and then we are going to use the probability distribution calculator. Okay, question 1. A Gallup poll of 1,236 adults showed that 12% of the respondents believe that it is bad luck to walk under a ladder. Wow. Consider the probability that among 30 randomly selected people from the 1,236 who were polled, there are at least 2 who have that belief. Given that the subjects surveyed were selected without replacement, the events are not independent. Can the probability be found by using the binomial probability formula? Why or why not? So let us recall the requirements for a binomial probability distribution. The requirements: number 1, the events must have a fixed number of trials, and the event should have a fixed number of trials. Number 2, the trials must be independent. Okay, the trials must be independent. Number 3, each trial will result in either a success or a failure. The outcome of each trial will either be a success or a failure. A success is a positive outcome, a failure is a negative outcome. We discussed those when we did probability. And the last one would be that the probability of success in a trial is the same as the probability of success in all the trials. Likewise, the probability of failure in one trial is the same as the probability of failure in all the trials. So these are the 4 requirements for binomial probability distribution, and of course for using the binomial probability formula. However, for the independent requirement, if you look at this here, given that the subjects surveyed were selected without replacement, the events are not independent. Of course, when we did probability, we discussed dependent events and independent events. Dependent events goes without replacement. Okay, those are dependent events. And then when you have the with replacement condition, they are independent events. Okay, dependent events goes without replacement condition. Independent events goes with replacement condition. So from what we see here, the condition, the trials must be independent, that requirement has been violated. However, we have what we call the 5% guideline. I'm gonna pull up my notes. Let's if you come here on this calculator, click on notes and videos. Let's look at notes. When we did probability, we talked about the 5% guideline for independent events. You remember that? So, can we treat dependent events as independent events in some situations? And the answer is yes. Why? 5% guideline for treating dependent events as independent events. So, this is stating that if the sample size is no more than 5% of the population size, then treat the selections as being independent. Okay, so the sample size must be at least 5% of the population size. Okay, let's get back to this question. I'm just gonna go ahead and pull up a calculator. I'll just pull up calculator. I'm using Windows here. For this video, I'm using Windows Machine. Okay, let's kind of look at this. You know what? I want this here, and then I want the calculator. So let's see whether we can treat this as it is dependent event, but let's see whether we can treat it as independent events. In this case, we would consider the population size to be the 1,236 people, and then the sample size 30 randomly selected people. So we are looking at 1,236 as the population size in this context, and the sample size as 30. Okay, let's look at that in this context. So let's take 5% of 1,236, and that will give us a 0.05 times 1,236, and that is a 61.8. Okay, then you ask yourself, is 30 less than or equal to 61.8, or is 30 greater than 61.8? Because if you look at this, the sample size should be less than or equal to 5% of the population size. And 5% of the population size is 61.8. And we see that 30 is less than 61.8. So because of that, we would treat this dependent event as independent event. Okay, let's look at the options. A, although the selections are not independent, they can be treated as being independent by applying the 5% guideline. That is correct. But let us look at the other options. B, yes, there are a fixed number of selections that are independent, can be classified into two categories, and the probability of success remains the same. Well, in this case, the fixed number of selections that are independent, no. These are dependent events, okay? Because it was done without replacement. They even said it here. The events are not independent. They are dependent events. So B is out. C, no. The selections are not independent. Okay, which should be so. But because of A, we saw that the 5% guideline makes A better choice. D, no, the selections are not independent and 5% guideline is not met. Well, 5% guideline is met. So you eliminate B and D. A and C are correct, but however, A is actually the correct choice because of the 5% guideline. Okay. Question 2. Determine whether the given procedure results in a binomial distribution. If it is not binomial, identify the requirements that are not satisfied. Surveying 100 married individuals and recording if they have ever been divorced. From the question here, it's a fixed number of trials. In this case, it's 100. The second requirement, the trials are independent. Nothing tells us here that they are dependent. Nothing tells us that they are dependent. Each trial is the outcome of each trial is either a success or failure. In this case, a success would be that they have not been divorced. Well, it depends on what you take as the success or failure. It just depends. In this case, you're trying to find out if they have ever been divorced. So the success might be that they have been divorced, and the failure would be that they have not been divorced. That is interpreting it. I'm not saying that divorce is nice. No, divorce is not good. But in this case, I'm trying to make you understand why we need to apply the binomial probability distribution, or why we do not need to apply it. So the requirements, I think so far has been met. Nothing here tells us that the event, that the samples, that it was done sampling without replacement, which would have made it a dependent event. But nothing here says so. They just surveyed them, okay, and recorded their responses. So I will say yes, all 4 requirements are satisfied. The 4th one is that the probability of success in one trial is the same as the probability of success in all the trials. So I will just say yes, all requirements are satisfied. Question 3 is the same thing, but a different question, but it's the same, determining whether the experiment represents a binomial experiment. An experimental drug is administered to 40 randomly selected individuals, okay, with the number of individuals responding favorably recorded. I will say that this the binomial probability distribution could is applicable here. Okay, all the because the experiment satisfies all the criteria for a binomial experiment. Question 4. Treating 200 bald men with a special shampoo and recording how they say their scalp feels. This might give us more than 2 possible outcomes. In this particular case, I think the binomial probability formula might not apply here, because if you're treating 200 bald men with a special shampoo, some might give a varied opinion about the shampoo. So I wouldn't say it is that the binomial distribution is applicable here, because you can have more than 2 possible outcomes. So I would go with A. I'm gonna go with A. Okay. Question 5. 3 cards are selected from a standard 52 card deck without replacement. The number of 5s selected is recorded. So this is without replacement, and then 3 cards are selected. So without replacement condition is for dependent events. However, the binomial distribution formula is applicable for independent events. We can take 5% of 52, because in this case the population size is 52 and the sample size is 3. So we can just do 5% of 52 and see whether we can apply the 5% guideline. So 0.05 times 52, and that is 2.6. So in this case, 3 is more than 2.6. 3 is more than 2.6, and denotes the sample size should be less than or equal to 5% of the population size. But in this case, 3 is more than 2.6. So no, it did not meet the 5% guideline, and it did not. First of all, it did not meet the independent trials requirement, that the trials must be independent, and then it did not meet the 5% guideline. So if we look at it here, B is out. I will go with D. It says no, because the trials of the experiment are not independent. Okay, and the probability of success differs from trial to trial. I'm gonna go with D. Okay. Question 6. 500 different voters in a region with 2 major political parties, A and B, are randomly selected from the population of 7,500 registered voters. Each is asked if he or she is a member of political party A, recording yes or no. So yes or no are the 2 outcomes. Okay, in this case, yes or no are the 2 outcomes But let us see this case is because 500 different voters in a region with 2 major political parties are randomly selected from this population. So from the way it's worded, it looks like it is it is without replacement. So let us see whether we can apply the 5% guideline. Our population size in this case will be 7,500 and the sample size would be 500. So let's do 5% of 7,500. 0.05 times 7,500, and that is 375. So but 500 is more than 375. 500 is greater than 375. Okay, we can only apply the 5% guideline if the sample size is less than or equal to 5% of the population size. So in this case, no, the trials are not independent and the sample is more than 5% of the population. So I will go with D in this case. Okay, now because we've not been doing calculations, so question 7. Multiple choice questions each have 4 possible answers, A, B, C, D, one of which is correct. Assume that you guess the answers to 3 such questions. A. Use the multiplication rule of probability to find the probability that the first C denotes a correct answer and W denotes a wrong answer. So multiplication rule to find the probability that the first question is correct, second question is wrong answer, and the third question has a correct answer. So correct answer on the first question, wrong answer on the second question, and a correct answer on the third question. We have 4 possible answers. So the probability of each is 1/4, one of which is correct. So the probability of correct answer is 1/4 because only one is correct, and the sample space, the cardinality of the sample space is 4, and you only have one correct answer. So the probability of selecting the correct answer is 1/4. You have 1 correct answer and 3 wrong answers. So the probability of selecting a wrong answer is 3/4. Does that make sense? Probability of selecting a correct answer is 1/4. Probably because you have only 1 correct answer out of the 4 possible answer choices. The probability of selecting a wrong answer is 3/4 because you have 3 wrong answers out of the 4 possible answer choices. So if we use the multiplication rule, for the correct one is 1/4, which is 0.25. Okay, 1 divided by 4 is 0.25. 3 divided by 4 is 0.75. So the probability that the first one is correct is 0.25 times the probability that the second one is wrong. Actually, they want us to type an exact answer. So 1/4 times 3/4 times 1/4. So correct answer is 1/4 times wrong answer is 3 over 4 times correct answer is 1 over 4. So 1 times 3 times 1 is 3 over 4 times 4, 16 times 4, 64. Okay, 3 out of 64. B, beginning with CWC, that is correct answer, wrong answer, correct answer. Make a complete list of the different possible arrangements of 2 correct answers and 1 wrong answer. Then find the probability for each entry in the list. For this one, wrong answer is 3 over 4 times 1 over 4 times 1 over 4. And that still gives us 3 out of 64. And this one is 1 over 4 times 1 over 4 times 3 over 4. That gives us 3 out of 64. Okay. C, based on the preceding results, what is the probability of getting exactly 2 correct answers when 3 guesses are made? We just add this here, these possibilities, the probabilities of these possibilities. So this is 3 out of 64 plus 3 out of 64 plus 3 out of 64. 3 plus 3, 6 plus 3, 9, because they have the same denominator. Okay, so this will give us 9 out of 64. Okay. Question 8. Assume that a procedure yields a binomial distribution with n equal to 6 trials and a probability of success of p equal to 0.80. Use a binomial probability table to find the probability that the number of successes x is exactly 3. In this particular video, we will not use tables. We are going to use my calculator and Statcrunch. So, but let's do this way. I do with my calculator. The next one you do Statcrunch. We do with Statcrunch. Next one we do with my calculator. Next question we do with Statcrunch. So let's say it that way. Let's do it that way. I'm gonna pull up my calculator here. And I'm gonna go to binomial distribution. Let's restore this. So I need binomial distribution. Okay, so I hope you can see this well. So in this case, we're gonna use this one right here. This one here. X is 3. N is 6 trials, and probability is 0.8. 0.8. Then press calculate. You can press calculate or you press the enter key. So the probability of getting 3 to 3 decimal places, like this is the one here, probability of x. Okay, 3 decimal places, that is 0.082. 0.082. Okay. Question 9. Statcrunch. Let's do this one with Statcrunch. Assume that a procedure yields a binomial distribution with 8 trials and a probability of success of 0.50. Okay, find the probability that the number of successes is exactly 8. Okay, we're gonna do this with Statcrunch. Well, actually, they say click on the icon to view the binomial probability table. So in this case, we will not use Statcrunch. No, I'm sorry. Yeah, they want us to use binomial probability table, which we are not gonna use in this video. We did that in other videos. We're gonna use Statcrunch here. So I'm gonna go to question help, and you select Statcrunch. Let's restore this, okay, so we can see this side by side. So you go to Start, Calculators, and you select Binomial. The number of trials in this case is N is 8 trials. Probability of success is 0.5. Okay, 0.5. And they want us to find exactly 8. Exactly means equal to. So you select equal to here, equal to 8, and you press compute. So to 3 decimal places as needed, the probability will be 0.004. Okay. Question 10. Assume that a procedure yields a binomial distribution with a trial repeated n times. So in this case, let's use my calculator. I can just click reset. X is 2, n is 6, and the probability of success is 0.55. And you can press the enter key. It will change the answers right away. So P of 2 is this one, and that is 0.186. Okay. Question 11. We can do this with Statcrunch. In this case, our n is 15, x is 4, p is 0.25. We can do it with Statcrunch. Question help, Statcrunch. So we go to Start, Calculators, Binomial. Okay. The n is 15, the p is 0.25, and x is equal to, you click here, make sure you select equal to 4, compute. So that gives us 0.225. Okay. Question 12, my turn. Refer to the accompanying technology display. The probabilities in the display were obtained using the values of 5 trials and the 0.724 probability of success. In a clinical test of a drug, 72.4% of the subjects treated with 10 milligrams of the drug experienced headaches. In each case, assume that 5 subjects are randomly selected and treated with 10 milligrams of the drug. Find the probability that more than one subject experiences headaches. Is it reasonable to expect that more than one subject will experience headaches? So let's see click on the icon to view the technology display. Let's make this bigger. So more than one subject, probability that more than one subject experiences headache. So I'm going to pull up this calculator. More than one, you can either add up from 2 to 5. Okay, the probabilities from 2 to 5. Or you can add the 0 and 1 and then subtract from 1. But let's make sure that, when we did probability distribution, you want to make sure that the sum of all the probabilities is equal to 1, right? 0.016, I suspect that they already did that. 0.016 plus 0.021 plus 0.1102 plus 0.2891 plus 0.3792 plus 0.1989 equal to. Okay, this looks like this didn't satisfy that because you have more than one. Let's do this again. 0.0016 plus 0.021 plus 0.1102 plus 0.2891 plus 0.3792 plus 0.1989. Okay, this satisfied it. Okay, I had to do it again. You gotta satisfy it to be 1. Okay, so with this question, what you could do is you could, because this says more than 1, so you can either add this, probability that more than that is 2 plus probability that is 3, probability that is 4, probability that is 5, or you can add this first 2, probability that is none, and the probability that is 1. You add it and subtract from 1. It gives you the same thing. So let's do that. We do 0.0016 plus 0.021, and then you now subtract from 1. So I'm going to put this negation here, this plus 1. You subtract from 1, and that gives you 0.9774. 0.9774. Okay. The next question: is it reasonable to expect that more than one subject will experience headache? With A, yes, because the event that the number of subjects that experience headaches is less than or equal to 1 is unlikely. And then C says yes, because the event that the number of subjects that experience headaches is less than or equal to 1 is not unlikely. The probability that more than one experience headaches is 0.9774. So it's reasonable because it's more than 5%. Okay, it's greater than 5%, so it's reasonable. Yes, because the event that the number of subjects that experience headaches is less than or equal to 1 is unlikely. Okay. Question 13. Refer to the accompanying technology display. The probabilities were obtained by entering the values. N is 5, P is 0.772. In a clinical test of a drug, okay, this is similar to what we just did, so let's click on this. The probability that at least 4 of the subjects experienced headaches. At least 4 of the subjects experienced headaches. So at least 4 means 4 or more. 4 or more. So this will be 0.4049 plus 0.2742. And that will give us 0.6791. 0.6791. Okay. Is it unusual to have fewer than 4 subjects experience headaches? Now, fewer than 4. Okay, so let's do the probability to have fewer than 4 experience headaches. We now do 1 minus this. So I'm going to do this, then plus 1. So this is 0.3209, which is 32.09%. Okay, so it is still more than 5%. So it is not unusual. No, it is not unusual. With that being said, we eliminate A and B, options A and B. Okay? So we look at C. No, because the probability that fewer than 4 subjects will experience headaches is not unlikely. D. No, because the probability that fewer than 4 subjects will experience headaches is unlikely. The probability that they will experience headaches is not unlikely, it's likely. Okay, so we'll go with C. Question 14. A brand name has a 50% recognition rate. Assume the owner of the brand wants to verify that rate by beginning with a small sample of 5 randomly selected customers. Complete parts A through D below. A. What is the probability that exactly 4 of the selected customers recognize the brand name? Let's get back to my calculator. Minimize this. Let's get back to using my calculator. So, in this case, from this question, I'm gonna reset this. Our X is 4, N is 5, and the probability of success is 50%, 0.5. Okay, 50% is 0.5. And you press calculate. So with my calculator, it gives you a lot of answers. So you now put in whatever you want. That is why I like my calculator. Probability that exactly 4 will be this. 0.15156. Okay. What is the probability that all of the selected customers, which means all 5 of them? So just change 4, press 5, and press calculate. All 5 would be 0.031. So 3 decimal places. 0.031. Then at least 4. I'm going to change this to 4 again. Calculate. You know what? We would have just used this. We would have just used, because this one is x equal to 5 or 5. That would have just been this. But that's fine. At least 4 is at least x. So to 3 decimal places, it is 0.188. Maybe you guys are not saying this. Let me bring it closer. Okay. 0.188 for at least 4. Then the next question, it says, if 5 consumers are randomly selected, is 4 an unusually high number of consumers that recognize the brand name? So exactly 4 of the 5. This gives us 15.6%. So that is more than 5%. So 4 is not an unusually high number, no, because it is greater than 5%. So the option will be D. Question 15. Let's do this one with Statcrunch. I'm just going to open up Statcrunch. Okay. So let's put in the values. You go to Start, Calculators, Binomial, and we put in the values. There is 0.8 probability chance, so the probability of success is 0.8. Assume 11 people are randomly selected. Okay, it says here, in a region, there is a 0.8 probability chance that a randomly selected person of the population has brown eyes. Assume 11 people are randomly selected. Find the probability that all of the selected people have brown eyes. So in this case, sample size is 11 and x will be 11. But you have to select equal to all. You select equal to and you click compute. Or you just, you click compute, it brings it. The answer is 0.086. Okay. Then exactly 10. N will now x will now be 10. X will now be 10 because that's exactly 10 of the selected people have brown eyes. So you put x equal to 10, press compute, and that gives us 0.236. Okay. C, find the probability that the number of selected people that have brown eyes is 9 or more. So x here, put 9. Now 9 or more is at least 9. So you come here, you click here, you select greater than or equal to 9. Okay, that is 9 or more. At least 9, greater than or equal to 9. And that gives us 0.617. D, if 11 people are randomly selected, is 9 an unusually high number for those with brown eyes? So we see here the probability is greater than 5%. So no, it's not. is not an unusually high number. No, because the probability that 9 or more of the selected people have brown eyes is greater than 5%. So I go with C. Okay. Question 16. My turn. 10 peas are generated from parents having the green-yellow pair of genes. So there is a 0.75 probability that an individual pea will have a green podge. Find the probability that among the 10 offspring peas, no more than one has a green podge. Is it unusual to get no more than one pea with a green podge when 10 offspring peas are generated? Why or why not? So we're gonna use my calculator. I'm gonna just reset this. Here the x is 1, the n is 10, okay, and the p is the p will give us 0.75, and just press calculate. This gives you the whole thing, okay? Probability that no more than one. No more than one means what? One or less, which means at most one. No more than one. Okay, we don't want anything more than one. No more than one. So it's gonna be one or less, and that means at most one. So you look at here, at most x, and to 3 decimal places it is 0.000. So I'm just gonna put only 0. Okay, I just put 0. Is it unusual to randomly select 10 peas and find that no more than one of them have a green podge? Note that a small probability is one that is less than 5%. Yes, it's unusual because the probability is very, very small. Yes, because the probability of this occurring is very small. Question 17. Researchers conducted a study to determine whether there were significant differences in graduation rates between medical students admitted through special programs and medical students admitted through the regular admissions criteria. It was found that the graduation rate was 96% for the medical students admitted through special programs in all medical schools. A. If 15 of the students admitted through special programs are randomly selected, find the probability that at least 14 of them graduated. Okay, let's do this with Statcrunch. Otherwise, I think I'll prefer my calculator. But let's do with Statcrunch. So we go to Start, Calculators, Binomial. In this case, the sample size is 15. The probability of success is 96%, which is 0.96. And at least 14, so put 14 here. At least 14 means 14 or more. So you come here, this is greater than or equal to 14. And that gives you 0.881. Okay. Suppose a medical school has 15 students in one of the special programs of its medical program. Does the probability calculated in Part A apply to these students? Well, in this particular case, if the medical school has only 15 students, then we wouldn't say it's a random sample. I mean, if all they had is 15 students, because if you look at the question A, it says if 15 of the students admitted through special programs are randomly selected, excuse me, we need to make sure that is a randomly selected sample. Okay, if the medical school has only 15 students only, then it's not a randomly selected sample. No, excuse me. So does this probability calculated in Part A apply to these students? No. Okay, so I'll go with B. No, because the students admitted through a single special program at a specific medical school are not a random sample. Okay. Question 18. Let's use my calculator. A TV show, Lindsay and Tobias, Lindsay and Tobias recently had a share of 25, meaning that among the TV sets in use, 25% were tuned to that show. Assume that an advisor wants to verify that 25% share value. Assume that an advisor wants to verify that 25% share value by conducting its own survey. And the pilot survey begins with 11 households having TV sets in use at the time of a Lindsay and Tobias broadcast. Find the probability that none of the households are tuned to Lindsay and Tobias. Okay, I'm gonna reset this. In this case, our X will be 0, none of the households. The sample size in this case is 11 households, and the probability of success is 25%, which is 0.25. Okay, and you press calculate. So P of X, none. This gives us 0.042. B, find the probability that at least one household is tuned to Lindsay and Tobias. At least one. So, at least one. So, with this X equal to 0, change it to 1. Press calculate and look for at least X. So at least one household, that will give us 0.958. At least one household, 0.958. Okay. C, find the probability that at most one household, at most one, will give us 0.197. Okay. D, if at most one household is tuned to Lindsay and Tobias, does it appear that the 25% share value is wrong? Well, you look at most one household, that is 19.7%. So it's greater than the 5%. So it's no. We eliminate A and D options. We look at B and C. No. For B, no, because with a 25% rate, the probability of at most one household is greater than 5%. Okay, that's right. Question 19. When someone buys a ticket for an airline flight, there is a 0.0984 probability that the person will not show up for the flight. A certain jet can seat 15 passengers. Is it wise to book 17 passengers for a flight on the jet? Explain. This is something that not only airlines do. Some transportation companies, they do it. They do what we call overbooking. Overbooking meaning that there is some probability that one or two people will not show up. So if they don't show up, they still wouldn't. The airline or the transportation company will not have to lose funds because they have people that will easily fill in those spots. So, but it all depends on probability. If in this question there is a 9.84% probability that the person will not show up, okay, and we want to overbook. So let's say for this with overbooking, you want to book 17 passengers for 15 seats. So let us find the probability that at least that this overbooking will work. So let's find the probability that at least 16 people will show up. Let's find that probability, and if that probability is high enough, then that means, hey, we don't need to overbook. I explain again. They gave us the probability that a person will not show up. Okay, a person who booked a flight will not show up. That's the probability. And they want to go ahead and overbook. So for overbooking to occur, that means this is a 15-seat flight, a 15-seater airline. For you to overbook, that means you have at least 16 people come. 16, at least 16, which means 16 or more. So let's find the probability of having 16 or more passengers show up for a 15-seat airline that was booked for 17 people. Okay, so this is what we're gonna do. Okay, I'm gonna do reset. Okay, I think it's turn off Statcrunch. That's fine. I'm gonna go to question help and pull up Statcrunch. So stats, calculators, binomial. The sample size in this case is 17 people that were booked. Now the probability we should be looking at here is the probability that they will show up. They gave us the probability that they would not show up. So the probability that they will show up will be 1 minus the probability that they will not show up. So 1 minus 0.0984 equal to, and that gives us 0.9016. So I'm going to come here and put 0.9016 as the probability of success. Now, overbooking will be at least 16 people. So greater than or equal to 16. And you press compute. So this is 0.49079313. It is still greater than 0.05. It's almost 50%. Okay, so the probability that that overbooking, the probability of booking at least 16 people on a 15-seat passenger flight that was actually booked for 17 people is high. Okay, it's greater than 0.05. It's 0.49. So that kind of tells you that people is gonna, that people will show up, and you don't want people to show up and then you have some people not get into the flight. That's one of the problems with airlines, and that causes confusion and chaos. So it is not. It's a wise decision not to overbook. Okay, it's not wise to overbook because of this probability is greater than 5%. So we eliminate B and C, B and D. B and D says it's a wise decision. No, because it's not a wise decision. Let's look at A. It is not a wise decision because the probability that there are not enough seats on the jet is this. So overbooking is an unlikely event. Overbooking is not an unlikely event because it's greater than 5%. Okay, it's greater than 5%. So we look at C. It is not a wise decision because the probability that there are not enough seats on the jet is 2 4 decimal places will be 0.4908. So overbooking is not an unlikely event. Okay. Question 20. My turn. A certain TV show recently had a share of 65, meaning that among the TV sets in use, 65% were tuned to that show. Assume that an advisor wants to verify that 65% share value by conducting its own survey, and a pilot survey begins with 10 households having TV sets in use at the time of the TV show broadcast. Find the probability that all of the households are tuned to the TV show. All of them. So, the X is 10, the N is 10, all the households, okay? And the probability of success is 0.65, 65%. And you press calculate. So probability that all of the households will be this or this. I mean, you can use this or you can also use this since it's all. So that the answer is 0.013. Okay. Find the probability that exactly 9 households are tuned to the TV show. So I place this as 9 and then I click calculate. Exactly 9 households will give us 0.072. Okay. C. Find the probability that at least 9 will be at least X. Okay, at least 9 households are tuned to the TV show. So that is at least X. That will give us 0.086. 0.086. Okay, continue. If at least 9 households are tuned to the TV show, does it appear that the 65% share value is wrong? Why or why not? So at least 9 households, that is the probability is 8.6%. 8.6% is greater than 5%. Okay, it is greater than 5%. So it does not appear that the 65% share value is wrong. No, because you look at only options A and B. We eliminate options C and D. So A, no, because 9 households tuned to the TV show is not unusually high if the share is 65%. B, no, because 9 households tuned to the TV show is unusually high if the share is 65%. It's not unusual, period. It's not unusual, it's usual. It's not unusual. So I'm gonna go with A. Okay. Question 21. The probability of a randomly selected adult in one country being infected with a certain virus is 0.003. In tests for the virus, blood samples from 22 people are combined. What is the probability that the combined sample tests positive for the virus? Is it unlikely for such a combined sample to test positive? Note that the combined sample tests positive if at least one person has the virus. Yeah, this is serious. Okay, let's go ahead, pull up Statcrunch. We don't want even one person to have the virus. We don't. So start calculators binomial. The probability of a randomly selected adult in one country being infected with a virus is 0.003. So P is 0.003. Blood samples from 22. N is 22 people. And they are combined. What is the probability that the combined sample tests positive for the virus? And note that the combined sample tests positive if at least one person has the virus. So X will be 1, but greater than, now in this case, at least 1 means greater than or equal to 1. Greater than or equal to 1. And that gives us 0.064 to 3 decimal places. Okay. Is it unlikely for such a combined sample to test positive? 0.064 is 6.4%, and that is greater than 5%. So it is not unlikely. No. It's not unlikely. So eliminate A and B. Let us look at C and D. C, it is not unlikely for such a combined sample to test positive because the probability that the combined sample will test positive is less than or equal to than 0.05. Is less than or equal to than 0.05. I think there's a typo here. Okay. D, it is not unlikely for such a combined sample to test positive because the probability that the combined sample will test positive is greater than 0.05. Okay. I go with D. Question 22. My turn. An airline has a policy of booking as many as 12 persons on an airplane that can seat only 11. So this is a policy. This is their policy. Okay. Overbooking. Past studies have revealed that only 84.0% of the booked passengers actually arrive for the flight. Find the probability that if the airline books 12 persons, not enough seats will be available. Is it unlikely for such an overbooking to occur? Alright, let's reset this. So in this case, 12 out of 12, even though it's 611, but for overbooking to occur, it must be it must be at least 12, okay, 12 or more. So, and they also told us here, find the probability that if the airline books 12 persons, not enough seats will be available. So our x is 12 in this case, our n is also 12. The probability of success is 0.84. 84% actually arrive for the flight. The other question we did was the probability of not showing up for the flight. That was why we had to subtract from 1 to get the probability of showing up for the flight. Okay. And you just press calculate. So that the probability for the x is 0.123. 1234 to 4 decimal places as needed. 0.1234. Is it unlikely for such an overbooking to occur? This is 12.34%. So it is not unlikely. It's greater than 0.05. It's greater than 5%. It is not unlikely for such an overbooking to occur because the probability of the overbooking is greater than 0.05. A. Question 23. A pharmaceutical company receives large shipments of aspirin tablets. The acceptance sampling plan is to randomly select and 12. The acceptance sampling plan is to randomly select and test 12 tablets. Then accept the whole batch if there is only one or none. One or none means at most one. Okay, if there is only one or none, that doesn't meet the required specifications. If a particular shipment of thousands of aspirin tablets actually has a 4% rate of defects, what is the probability that this whole shipment will be accepted? So accept it if at most one is has defects. Accept it if at most one has defects. Okay, let's go to Statcrunch. So start calculators, binomial. The sample size there is 12. The probability of success, which is the rate of defect, is 0.04. That is 4%. And we want at most one. At most one is 1 or less. At most 1. Okay. So you press compute. So the probability that this whole shipment will be accepted is 0.919 to 3 decimal places. 0.919. Okay. Question 24 seems to be almost the same. We can go ahead and do this with Statcrunch again. N in this case is 17. P is still 0.04. And at most 2 tablets. At most 2. At most 2. 2 is 2 or less. Okay. You press compute. And that gives us 0.971. Right? Okay, I think we've done the calculations. The rest are just answering this. Okay. Which of the following is not a requirement of the binomial probability distribution? Probability of success is the same, remains the same in all trials. That's correct. Trials must be dependent. No. Okay, the trials must be independent. Procedure has a fixed number of trials. That is right. Each trial must have all outcomes classified into 2 categories, success and failure. So B is the answer here. 26. If calculations are time consuming and if a sample size is no more than 5% of the size of the population, they dash states to treat the selections as being independent, even if the selections are technically dependent. Yeah, this is called 5% guideline for cumbersome calculations. 27. In the binomial probability formula, the variable x represents the number of successes. Okay, number of successes. N is the number of trials. X is the number of successes. Question 28, last but not the least. Which of the following is not one of the 3 methods for finding binomial probabilities that is found in the chapter on discrete probability distributions? Use a statistical table for binomial probabilities. That's right. Use a computer software. That's Statcrunch. Statcrunch is a software. Or a calculator. That's my calculator. My calculator. That's right. Use a simulation now. And use the formula, binomial probability formula. That's right. So the answer is use a simulation, which is not one of the 3 methods. Okay, and you can go ahead and save this. Thank you so much for listening to this video presentation. If you have any questions, please feel free to ask. And you have a good evening.